Yeah. Okay, so yeah, thanks for inviting me to talk. So I'm going to tell you about our ModFOLDdock method, first of all, and then I'm going to answer some of the questions, the specific questions that were sent to us before the meeting. So we were emailed questions to answer. So yeah, we developed 3 different variants of ModFOLDdock. They were optimized for different facets of the model quality estimation problem. So first of all, we have ModFOLDdock. And these global scores were optimized for positive linear correlations with the observed scores. Secondly, we've got ModFOLDdock-R, and these global scores were optimized for ranking. So the top ranked models should have higher overall accuracy in terms of observed score. And then finally, we've got ModFOLDdock-S, which is a quasi-single model approach to score models. And in this version, sets of reference models were firstly generated using our MultiFOLD method, and then each model was then compared individually against the reference model set. So we optimized our methods for using the CASP15 multimer dataset, and our target functions for optimizing were shown at the bottom of the slide there. So these were based on the assessor's formula for CASP15 multimers. So for local or interface scores, we use the interface contact score and interface patch scores from the CASP15 data. And yeah, sorry, that's sorry, did you forward those on? Did you forward that on? Sorry. Yeah, so sorry, go back to the target functions there. So at the bottom there, so those are the local scores, the interface scores that we optimized for, and then the global scores were the used for the overall fold, and this was oligo, LDT, and TM score. Okay, so each variant was made up of various different combinations of component scores, which are listed here. So we used the 5 different consensus-based methods, which carried out all against all comparisons using different scores. So we've got the .q jury score, where this basically uses .q to score equivalent pairs of chains between models. Then we've got 2 variants of QS score. We've got QS score jury, QS score official jury, basically 2 different versions of the QS scoring method. We've got LDT official jury, which uses the oligo LDT score, and ModFOLD IA, which uses our in-house interface accuracy scoring, which is a little bit like LDT, but for interfaces. And we also use 2 different single model scoring methods, Voronota, VORA-MQA, and the CDA score, which stands for Contact Distance Agreement Score. And we use the contact prediction profiles from CollabFold for that. And finally, we also used a quasi single model scoring method, which made use of reference sets of models generated by a MultiFOLD method. And obviously here, the single model is then compared against 30 reference models, which are generated using MultiFOLD, which I'll tell you about more shortly. So basically, we had 3 variants of ModFOLDdock, and each variant needed 3 sets of scores. So the figure on the right of the slide basically shows the different scores that were required for the QA, QMode2 files for each target. So firstly, we had the fold score, which represents the accuracy of the overall fold or the assembly accuracy for each model. Secondly, we had to generate the interface score. This represents the overall accuracy of the interfaces between all of the subunits. And then finally, we've got the scores for each residues, which represent the probabilities of each residue being in the interface. So each variant has 3 sets of scores which go into the QA file. And these are listed on the left for each variant, but obviously it's actually easier to visualize these things as flowcharts. It's more informative to show the inputs, the methods, and the outputs, and how they're all connected. So that's what I'm showing on the next slide here. So this is a flowchart showing the data and processes for the ModFOLDdock method. So just to break it down into sections, on the left, we've got the inputs, we've got the methods in the middle, and then we've got the outputs on the right-hand scores. And highlighted in green on this slide are basically the components that contribute to the overall scores for ModFOLDdock. And the arrows indicate how they contribute to each score. So the .q and QS score contribute to the overall interface score in this case, while the .q and LDT score contribute more to the fold score. And in this variant, the residue scores come purely from the ModFOLD IA method. So that's a ModFOLDdock variant. The ModFOLDdock R variant is similar, but we use slightly different components. So we've now got the integration of single model methods, and we've got extra residue scores. The interface score and the fold scores are use the same components as the ModFOLDdock variants, but use different components to the ModFOLDdock variant. But we've also got the Vora MQA score as well, which contributes to the residue scores as well as to the global score there. So there's a slight difference in the component methods. And next we got the flowchart for the ModFOLDdock S variant. Again, slightly different components are used here. We also have the integration of single model methods and extra residue scores. Here, in this case, the interface and fold scores are the same as the ModFOLDdock variant, but we've also got the local scoring methods. We've got all local scoring methods combining to produce the residue scores. And importantly, this variant also uses the quasi single model approach that relies on the generation of reference models from our MultiFOLD method for model comparison. So what is MultiFOLD? So this is a flowchart showing the MultiFOLD method. There's three basic stages to this. The first stage is the generation of models using two different versions of a local collab fold. And the next stage is to rank these models using ModFOLDdock, and then you select the top 5. And then you use those top 5 models as template input files to local collab fold 1.3, and then you do a number of recycles. And the reason we've got two different versions, excuse me, of local collab fold is because they use two different approaches to the assembly prediction. They use different sets of weights, and in some cases, version 1 is actually produces better multiple predictions than 1.3. So by including both versions, we make the overall approach a little bit more sort of orthogonal. Okay, so that's a method. So I'm going to now try to attempt to answer some of the assessors' questions. So they sent, Gabriel sent us the questions before the meeting. And firstly, the first question was, where do you think you're particularly good? So in order to work this out, we first thing we did was to calculate all the observed scores for the models and then plot them against the predicted scores for all models. So here we have the predictive fold score versus the oligo LDC score for all homomeric targets. And if you calculate the correlation coefficients, the initial scores don't seem great, but you can actually see that there's some outliers on the plots here. There's an obvious set of outliers. So these are for the models T1160 and T1161. Which the assessors told us beforehand have similar sequences but different conformations due to crystallization conditions. So it's not surprising that these were difficult to score, as these basically two different correct answers for essentially the same target. So how we deal with this issue for model accuracy estimation is a problem that we need to handle in the future. And obviously, if we just leave out these targets, we get much better correlations overall. Okay, so this next slide basically shows the same thing, but for heteromeric targets. Again, the correlations initially seemed a little bit disappointing to us, a little bit low, but then obviously there was these outliers here, which are H1171 and H1172. And again, the assessors told us that H1171 and H1172 can come in multiple conformations. I think 7.2 can come in sort of 4 or more different conformations. So again, this data on the slide is not valid because here we only scored the models based on the first conformation to get the observed scores. So really, we obviously need to deal with this when evaluating performance. But again, if we remove these, we then get better correlations. So I've done this for all the scores, all the scoring methods. And my students helped me try and do this just before we had to leave. So this is a table of the summary of correlations between predicted and observed QS and oligo scores for all targets, obviously excluding the targets with the alternative conformations, and 2 targets that failed because of chain mapping errors, which we couldn't fix in time before the meeting. So basically, this shows that the scores that are tuned for interfaces do well at the QS scores, and the scores that are tuned for fold or assembly do very well for oligo LDC. So this is essentially what we expected. We also expected that ModFOLDdock would perform the best overall on the correlation metric, because that's what it was tuned for. That's what we designed it for. And the data also shows that the single model methods that we used are not so good at the correlations, but perhaps they're better at ranking the top model, but we don't have that data yet. So yeah, these are the next questions that were asked. So what are the added challenges of assemblies versus single chains? Where do you see problems and lessons learned? So the main real challenge with this was the size of some of the structures. So this gave us a real challenge to balance the load on our servers so we could meet the 48-hour deadline. So we did all of our predictions for the whole of CASP on 2 servers with A10 GPUs. So our goal was to make methods that were sort of lightweight, that could work on single servers, and this is so they could be shared and distributed more widely. So they needed to be able to work well and be relatively lightweight as well. So yeah, that was a major challenge for at least the large structures. Another issue was the general parsing problems, unforeseen issues with scoring multiple chains. For instance, obviously the chain mapping problem, which Gabriel's already told us about. We had to deal with that as well, and other things like missing chain IDs, out of sync chain IDs. People were submitting all kinds of different combinations of chain IDs and leaving them out and whatever. So we needed to handle all of this before we could even start doing the scoring. So there's a lot of parsing to do before scoring. Unknown target functions, we didn't really know what we'd be optimizing. So we kind of guessed based on the CASP15 assessors formulae beforehand. There were no real gold standards for interface residues, so we were kind of in the dark about that before we started. We had 3 different scores to optimize this time versus monomers. So we've got the global or fold or assembly score, but we've also got the global interface score, and we've got also the local interface residue scores as well. And in future, we'll probably combine sort of quasi model methods with single model approaches, similar to our ModFOLD9 approach for monomers, which we've developed recently. And this will reduce our computational overheads significantly, I think. So we won't need to do these sort of massive all against all comparisons of massive structures, and we'll bring in more deep learning methods next time for combining the component scores as well. So finally, so how does your method differ from state-of-the-art methods in the field? And would you gain anything from detailed knowledge of the modeling process? Okay, so the other top methods are listed here. So these are descriptions based on the abstracts. So obviously we've got multicom, which we'll hear about in a minute. Consensus method, it uses MMAlign comparisons. There's VORIF, which we'll also hear about, a graph attention network. RocketX, which we've just heard about, based on deep UMQA, another single model method based on deep learning. And our ModFOLDdock approach overlaps with different aspects of each of these different methods. So we use consensus methods, but we use with different scores. We use single model methods, including VORIMQA, and we also use some deep learning with our methods, our CDA method and our sort of MultiFOLD based methods, which are also integrated. And yeah, and I think that quality estimates should be largely kept independent. So knowledge of the model processing method and the self-assessment shouldn't influence the independence of the quality scores. I don't think we need to know anything about how the model was made before we score it, essentially. So that's my take on it. But obviously, we've probably discussed that a bit more later as well. Yeah, so just to thank my group members, my PhD students, Nick, Shwa, and Amit, who are funded by their governments, and they're sitting in the back over there. My postdocs, Recep and Virginia, who can't be here, they're funded by the BBSRC. The MultiFOLD and ModFOLDdock web servers will be available very soon at those URLs. And you can also download the Docker version of MultiFOLD, which integrates ModFOLDdock. from our Docker hub as well. And finally, we've got we just released a preprint on bioRxiv, talking about the sort of recycling process for the improvement of models, which is used by a MultiFOLD method. And that's it.
Thank you, Liam.
Thanks for listening.
Thanks.